Assalamu alaikum. I welcome you all to another topic on power electronics. Today, in this topic, we will discuss the double ended forward converter and we will see how the topology presented in this converter has improved the performance of a single ended forward converter. So, let us first of all draw the diagram of a single ended forward converter, or otherwise known as simply a forward converter, and we will then analyze the problems associated with the leakage inductance present in it, and then we will draw the circuit diagram for a double-ended forward converter, and we will analyze how this double-ended forward converter has actually solved this problem. So let us start. So this is the topology of a single-ended forward converter, and here we will draw the topology for a double-ended forward forward converter. So single-ended topology consists of a voltage source and a transformer. So the problem with the conventional single-ended forward converter is that any leakage inductance associated with the winding here, which is sometimes referred to as the LK, during the demagnetization of the core or the resetting of the core process, there is no way that the current flowing through this LLK can be freewheeled. So the problem here is that there is some current flowing here, and this current is the ILK, and this is the same current that is flowing through this magnetizing inductance LM and the primary winding current I1, and this actually goes through this leakage inductance which is present in the primary side, or which is referred to onto the primary side. The problem associated here is that once we turn off this switch, then this switch has to endure some voltage that it has to block. Now this LLK has some current ILK flowing here. That means that when this switch is turned off, this DILK over DT, it goes to infinity. Now why it goes to infinity? Because unlike this magnetizing inductance that has a current path to flow through this through this primary side winding, this current which is flowing through the leakage inductance has nowhere to go, and therefore it will create a high voltage, which is this VLK, and that creates a voltage spike across this switch here, and therefore the voltage stress on the primary side switch is much higher than the one that we anticipate through the theoretical design, and this can lead to the failure of the switch which is connected here. So in order to solve this problem, a double-ended forward converter topology is proposed. This double-ended forward converter topology has two switches that are used to drain the transformer core to zero once the process of demagnetization of the core initiates. The second thing here is that instead of using one switch, we use two switches, and therefore the voltage stress experienced by a single switch becomes half of that what we have seen for a single-ended forward converter. So let us draw the diagram of a double-ended forward converter, and thereby we will start the analysis for the turn on state and the turn off state, and then we will derive the voltage gain of this given converter. So here the we have a voltage source The secondary side is same as that of the single ended converter, where we have an output filter consisting of these inductance Lx and this capacitor C naught. Here we have this V naught. So this is the diode D1, this is D2. This diode is designated as D3. Let us say this is D4. This is switch S1, this is a switch S2, and this is the topology of a double-ended forward converter. Now, if you notice in this given converter, we have two switches S1 and S2 that must be operated simultaneously in order for the current to flow through the magnetizing inductance Lm as well as the primary side winding N1. So we have a current here. This is the current I1. This is the current IL, and therefore these switches S1 and S2 must be operated at the same time. The secondary side of this double-ended forward converter works exactly in the same way as we have seen for a forward converter, or simply known as a single-ended forward converter. So the only difference comes in the operation of the primary side. So let us analyze this circuit based on its switch state, and let us see what are the states that are witnessed in this converter. So the first thing here is that the switch S1 and S2, they conduct at the same time. When this happens, when this S1 and S2 are conducting, then the diodes D3 and D4, they will remain reverse biased, as we will shortly see. So during this time, this switch D3 and D4, they remain off when S1 and S2 are on. The third thing here is that when D3 and D4 conducts, then S1 and S2 are turned off here. So let us analyze this circuit. We will draw the equivalent circuit based on the duty ratio applied to a double-ended forward converter, and we will see that what happened when we turn on the switches and when we turn off the switches, what is the equivalent circuit, and let us see that thing. So the first thing here is the let us say this is mod 1. Mod 1 is then S1 and S2, they are turned on. So S1 and S2, when they are turned on, let me copy this this given circuit, so that will save our time. Okay, so here we have this thing here. Okay, so when we have this S1 and S2 turned on, then this becomes short circuit path. When this path is short circuited, this point of D4, the anode of D4, it gets connected with the negative side, and therefore this D4 turns off. On the same time, on the same basis, we can see that when this switch S1 is on, the cathode of diode D3 becomes connected with the positive of the supply voltage Vs, and therefore D4 and D3 will turn off. Now if I just remove them from this thing, just to ensure that we don't have a clutter here. So this is what the circuit on the primary side looks like. So on the secondary side, we have this D2 is off and this D1 simply conducts, and therefore this is the circuit during the time S1 and S2 are on. Okay, so now during this time we are interested in a few things. For example, I am interested in knowing what is the voltage here. Let me call this VLM, or we can say that is also equal to V1. I'm also interested in knowing the voltage. This is the voltage V2 and the voltage across the magnetizing, across the inductance VLX, which is basically the inductance of the filter circuit connected onto the secondary side here. So if I apply the knowledge of the basic circuit analysis, we can see that this V1 is equal to this Vs, and that is equal to VLM. The voltage V2 here is given by using the turn ratio concept of the transformer, that is equal to V1 into N2 over N1, and that is equal to Vs into N2 over into over N1. Okay, other than that we have the VLX. So VLX is equal to, we have to apply the KVL on the outer loop. So it gives me VLX equals to V2 minus V naught, and because this V2 is equal to Vs into N2 over N1, so this becomes equal to Vs into N2 over N1 minus V naught. Similarly, on this side, we have developed some equations, and we do know that this VLX is nothing but that is equal to L DILX over dt, and therefore I can rightly say that when we have turned on the switches S1 and S2, the rate of change of the current flowing through the inductance Lx can be categorized or can be summarized as delta ILX when the switches are closed. That becomes equal to the Vs N2 over N1 minus V naught over Lx. And this is the time when we have turned on the switches S1 and S2. Now on the same pattern, we can develop the equations for the mod 2 here as well. So let me use a different color just for the clarity. Okay. So during the mod 2, the circuit looks like, let me again paste the circuit here. So let me draw it here somewhere. Okay. So you are turning off the switches S1 and S2, and when S2 and S2 are off, that means that there is no current flowing here. So this is gone. Similarly, this S2 is open circuited. Because there is no current flowing through the primary winding now, therefore the diode D1 will also become reverse bias, and therefore this becomes open circuit. So the point here is that we have a current in ILM that will flow through this path. This ILM will see that there is a current flowing through this path. It will go through this one, through this diode D4, goes into the positive terminal of this Vs, comes out of this negative terminal through this D3, and then this is the path of the inductor. This is the part of the inductor current here. So now if you notice here that the voltage V1, which is across this V1 has a dotted end connected with the negative of this Vs, whereas the non-dotted end of the primary winding is connected with the positive of this Vs. Therefore, the voltage V1 is equal to minus Vs here, VLM as well. So the voltage across the magnetizing inductance of this topology VLM is DILM over dt is equal to minus Vs, okay, is equal to minus Vs over Lm here, right. On the other side, the current which was flowing through this Lx shall have its path freewheeling through the diode D2, and therefore if we apply the voltage here, then the VLX is equal to minus V naught, and that is equal to L DILX over dt, and this gives me that this DILX over dt is equal to minus V naught over L. So we have now enough equations, and by the way, this is nothing but that is equal to delta ILX when the switches are open here. So now that we have established these equations, the next thing is to develop the inductor volt second balance, or through the common expression that in a steady state the net change in the inductor current is equal to 0, and therefore we can simply add the delta ILX open and delta ILX closed and equate them equal to 0 to derive the voltage gain of this given converter. So the delta ILX close plus delta ILX open must be equal to 0, and therefore this becomes equal to Vs N2 over N1 minus V naught into D minus V naught into D dash, that is equal to 0. And if I solve this thing, I will get that this V naught over Vs is nothing but that is equal to D into N2 over N1. And this is the same expression as that of a single-ended forward converter. However, once we have we done with this voltage gain expression, we should now have a look onto the maximum duty cycle that can be applied on these switches S1 and S2. Now, notice here we should note one thing through this given equivalent circuit, that the slope of the ILM during the time when we have turned on the switches S1 and S2 is equal to Vs over Lm, right? It is Vs over Lm. So the slope for this magnetizing inductance current is Vs over Lm for the time turn on, while the slope is minus Vs over Lm when the switches are open. And because the slope is exactly the same for the turn on time as well as for the turn off time, therefore, in order to fully reset the core, or in order to fully demagnetize the core, the maximum duty ratio that can be applied onto switch S1 and S2 must be less than 0.5. So let me write this fact here. Since the slope of ILM is Vs over Lm during on, and minus Vs over Lm during off, we can set D equals to 0.5, and this is the maximum that what we can do. So it must be equal to 0.5, cannot be greater than 0.5, otherwise it will have an accumulative effect and the current will continue to rise in a very few cycles. It will go into the into a very high value. So we can set D equal to 0.5, and for simplicity or for safety, usually this D is set less than 0.4 for safe operation, right? So for safe operation we keep it below 0.4. Now the question here is that if it is 0.4, then how can we assure that the output voltage is always according to our requirement? So there comes a factor that we set the value of N2 such that we set the value of this, if this is for example, if this is N1 and this is N2. So what we see is that we set the value of N2 such that the peak voltage for the duty ratio D equal to 0.4, it suffices the requirement of the output voltage. So here what we have seen, that using this given topology, now let us have this again have a look onto the circuit here. Now if you assume that we have some leakage inductance LLK here, this magnetizing inductance now has a path to drain its current down to 0 through the diodes D4 and D3, and therefore there is no extra voltage stress applied onto the switches S1 and S2 because of the leakage inductance of any given transformer, and therefore this problem is solved. The other beauty of this converter is that the switch stress on the switches S1 and S2 is half compared to the single-ended forward converter, right? So compared to the single-ended forward converter, the voltage stress is half. However, the gating requirements are more because with this topology we have to operate two switches, which one is connected on the higher side and another one is connected on the lower side. Whereas for the single-ended forward converter, with the use of an extra winding, we relied on only using a single switch for the entire operation of the converter. Thank you very much for listening. Allah Hafiz.